Good morning, everyone. Myself, Dr. Amish Srivastava. I'm professor in CSE department, SIRT, Bhopal. So let us now start with our module 2 of operating system. This is a lecture 1. So here we will be seeing different memory management techniques, partitioning, swapping, segmentation, etc. So basically in this module, we will be covering the background, swapping, what is swapping, continuous memory allocation, what is paging scheme, structure of the page table, segmentation, demand paging, copy on write, page replacement, and different algorithms for page replacement, allocation of frames, thrashing, and other considerations which we do. So mainly the objective of this module is to provide a detailed description of various ways of organizing memory hardware, to discuss various memory management techniques, including paging and segmentation, and to provide a detailed description of segmentation with paging. So the basic hardware which is involved here is the main memory and the registers, and they are the only storage which can be accessed directly by the CPU. Program must be brought from the hard disk into the memory and placed within a process for it to be run. Registers are the fastest memory in our computer system, and they can be accessed in one CPU clock cycle. But if our data is present in the memory, on the main memory, then it might require several memory cycles for the CPU to access that data. To compensate for this delay, there is another memory, cache memory, which sits between the main memory and the CPU registers. So for speeding up the things, and the protection of memory is also required to ensure the correct operations. So these are two registers, base and limit registers. They operate in the privileged mode. There is basically two different types of modes in our operating system, privileged mode and non-privileged mode. So in privileged mode, user is not allowed to do any activity, whereas in non-privileged mode is also known as the user mode. Here, user can perform different activities which we normally do. So this base and limit registers are loaded by the operating system in the privileged mode. That is, user don't have any authority to load this base and limit registers. Now, suppose, for example, we are having 3 processes in our main memory right now. Operating system is there, and this blue shaded area is a free space. Fine. So suppose this second process starts from 30040 and it ends at 420940. So the base register will hold the address of the first instruction or first line of this particular process, which is 30040. And limit register tells us what is the total size of this program. How we can obtain it? Simply, we will subtract this 30040 from 420940. Fine. So this is our limit. It is coming to be 120900. Now, how this base and limit register helps? It helps in protection of other user space, because whenever the process generates any address for execution, then it will be checked whether that particular address, address which is generated by the CPU or by this process is higher than this base address. Let us say that the CPU generates or this program generates the address 30050. So we will check, or the operating system will check whether this 30050 is greater than this base address. Yes, it is greater than. And second check will be whether it is less than 30040 plus 120900. It simply means that it should be less than 420940. So we have generated the address 30050, which is in between both these addresses. So it is a valid address and it will be executed. But suppose the process is a malicious program or it's a virus, then it might generate the address which is beyond the limit of this particular process. Let us say it generates the address 420960. So what will happen? This address is greater than this 420940. So operating system will not execute that statement and it will simply terminate that process. So basically this base and limit registers are utilized for protection of user space. Okay. Now next is address binding. Basically there are two types of addresses in our CPU. One is the logical address and another is the physical address. Now let us see. Okay. So what is the user address, logical address, and what is the physical address? So the memory, this memory addresses are known as physical address. It means this process has got the memory address starting from 30040 and it ends at 420940. This is the physical address. That is the address of the main memory where this process is loaded. Now, the logical address is simply the numbers. Like suppose I have got 10,000 lines of code for my program, then the starting address will be 0, then the next line will be 1, next line will be 2, 3, 4, till 10,000. So this from 0 to 10,000 will be our logical address, and the physical address is the main memory where our process is loaded. It is definitely logical and physical addresses will be different. Okay. So we have to bind the addresses. Binding means binding the logical address to the physical address. So this kind of address binding can be done at 3 different times: compile time, load time, and execution time or runtime. So binding of instructions and data to the memory, address binding of instructions and data to memory addresses can happen at 3 different stages. Compile time, if memory location is known in prior, then absolute code can be generated at compile time itself. Means what? That if I already know that this process will be loaded into the memory location from this address to that address, let us say the previous example, if we already know that this process 2 has to be loaded from 30040 till 420940. So what I will do at compile time itself, I will generate the absolute code. I will not generate the logical address. I will simply generate the memory address, physical memory address, because ultimately they will be the addresses which will be accessed for execution purpose, right? So in that case, what I will be doing, I will be generating that memory physical address itself at the time of compiling the program. So what is the disadvantage of this? Doing this, mapping the logical address to the physical address at compile time, the disadvantage or the problem is that if at runtime we are required to change the program's memory location, then we must recompile the code. It means what we have to do, we have to again simply delete the program or process from the main memory. We have to recompile it. Again, we have to link all the libraries and then it has to be loaded for changing the physical address of our process or program. So it will take a lot of time, obviously. Nowadays, we don't dedicate the CPU completely to only one process. There is a multitasking processes. The CPU is shared among different processes. So after certain small interval of time, the CPU will be switching to another process and so on. So let us say our 50% of the code has been executed, and after that, the program or process needs to be shifted in the main memory for freeing up the space. We will discuss this kind of technique, what is why we are required to shift the process into the main memory at runtime. That we will discuss later on in the later lectures. So we have to shift it. So if we have to shift it, then 50% of the code has already been executed, and then we again have to recompile it. In that case, the whole execution, that is 50% execution, will be wasted. Also, it will take much time for again recompiling, linking, and loading it. So this is a problem. Similarly, if we know the physical address at the time of load time itself, then what we will be doing, we will be generating the relocatable code if memory location is not known at compile time, and actual address binding is done. So if we are not knowing the physical address at compile time, then what we can do, we can bind the logical address to the physical address at the time of loading. Again, the disadvantage is same. If we need to shift the process in the main memory at runtime, then we will require to reload the program. Here we don't require to recompile the program, but reloading will be required, and this will again take a lot of time. So binding of instructions and data to memory at execution. So binding is delayed until runtime if the process can move during its execution from memory segment to another. This will need some hardware support for address mapping. That is, we will be mainly requiring the relocation. It means the third kind of binding is execution time binding. So here we don't bind the logical address to the physical address until we start executing that process. Okay. Let us see this concept. So logical versus physical address space. The concept of a logical address space that is bound to a separate physical address space is central to the proper memory management. Logical addresses are the addresses generated by the CPU, also referred to as virtual addresses, and physical addresses are the addresses seen by the memory unit. Logical and physical addresses are the same in compile time and load time address binding scheme, whereas in the logical or virtual and physical addresses differ in execution time address binding scheme. So memory management unit consists of hardware devices that maps virtual to the physical address. In MMU scheme, the value in the relocation register is added to the every address generated by the user process at the time it is sent to the memory, and the user program deals with the logical addresses. It never sees the real physical addresses. So let us look at this whole concept in this figure. So in execution time binding, when the program changes its memory location, we only need to change the value of the relocation register for mapping the logical address to its correct physical address. Let us say now our CPU has generated the logical address 346. So basically this 346 is nothing but the 346 line number of our process. Okay, because the numbering always starts from 0 or 1. So 346 must be the 346 line number of our process. But it is simply the logical address. We have to first of all map it to the physical address for execution of that statement, because in the physical memory or in the main memory, it might be lying at somewhere else. So if we say that execute 346 address or 346 line of my process, then the CPU or then the operating system needs to know where this 346 line number is lying into the physical memory. Then only it will be able to access it. So let us say our base address of our process is 14,000. So what I'm going to do is we will load this relocation register with the base address of that particular process. That is 14,000. Now, if I say 346 line number, that is 346 starting from 14,000. So what we have to do, we will simply add this 14,000 to 346 to get the physical address, that is 14,346. So in this case, what will happen if we need to shift our process from say 14,000 location to, let us say, 10,000 location. So what we need to do, we don't require to recompile or reload the program. We simply require to reload this relocation register. We will simply reload it with the value 10,000. So the upcoming next addresses will be simply added with this 10,000 to get the actual physical address. So this is the concept for runtime or execution time address binding, and it requires very less time. Simply we need to reload this relocation register. Again, this loading of the relocation register is done in the privileged mode. So now next is dynamic loading. All routines are kept on the disk in a relocatable load format. The main program is loaded into the memory and is executed. When a routine needs to call another routine, the calling routine first checks to see whether the other routine has been loaded. If not, the relocatable linking loader is called to load the desired routine into the memory and update the program's address table to reflect the changes. Then the control is passed to the newly loaded routine. So what is basically this dynamic loading is, let us say I've got a program and it contains 10 different libraries. Now, or 10 different, it has got 10 different functionalities or the exception handling codes. Fine. Now, if my process has got 10 different exception handling codes, then it is not necessary that all the 10 exceptions will occur when we will run the program. So it means that we don't require all these 10 exception handling codes all the time. We will require them only if some kind of exception occurs in the program or during the execution of the program. Let us say divide by zero error. So this is one exception, and I have written some code, let us say, for handling this kind of exception. So I have written 10 different types of code for this kind of exception handling. So what we will be doing, we will be simply loading the main program into the main memory, and we will not load this 10 exception handling modules initially. So what we are going to do, whenever some kind of exception occurs, then dynamic loading concept will be used. For this relocatable linking loader, first of all, we will check that whether this particular exception handling module is present in the main memory or not. If it is not present, then what this relocatable linking loader will be called to load the desired routine into the memory from the hard disk at the runtime. So that is why the name dynamic loading. So what is the advantage of this? Better memory space utilization. Unused routine is never loaded. So a large program consisting of many infrequently required routines will require only small space in the physical memory. Also, it will run faster because we don't have to load the complete large program. We will be loading only the main functionality. And whenever some kind of routine is required, then we will load it at dynamic time or runtime. So the starting time of the process will also be very fast. It is useful when large amount of code are needed to handle infrequently occurring cases such as error routines, and no special support from the operating system is required. In this case, it is implemented through program design by taking the help from library routines to implement dynamic loading. Similarly, dynamic linking concept is also there. So here, linking is postponed until the execution. This feature is usually used with system libraries. Without this facility, each program has to keep its own copy of the system library, which wastes a lot of memory. With dynamic linking, a stub is included in the image for each library routine reference. Stub is a small piece of code which is either used to locate the appropriate memory library routine or how to load the library if the routine is already not present in the memory. Stub replaces itself with the address of the routine and executes the routine. This system is also known as shared libraries. So for example, let us say I have loaded 10 different C++ programs into the main memory. Now, all of these programs will be requiring iostream.h header file for input output, right? Conio.h and some common libraries. So if I am loading 10 programs of C++, then I will have to load these libraries also. So what is the utility if I load these iostream.h, conio.h library 10 times for 10 different programs? It is simply a waste of memory. So what concept we are using here is dynamic linking concept. It means that the first program, when loaded, along with that, the libraries will also be loaded. Now, after that, libraries will also be loaded, or even they are not loaded, then what will happen? The libraries at runtime, whenever the libraries are required, then the stub, which is a small piece of code, will check whether that particular library is present in the main memory or not. If it is not present, then it will simply use the dynamic loading concept and reload it. And once it is loaded, then the second process, which requires this library, again, this stub will be checking whether it is present in the main memory or not. So if it is present, then it will simply link that existing library to its own process. So the redundant copy of the library need not be loaded. It will save obviously a lot of space. Okay, so that is all for this lecture. Next, we will see in the next lecture. Thank you.